We said earlier that we currently know 118 chemical elements, of which 94 occur naturally on Earth. In the previous video, we talked about elemental substances that are made of atoms of a single chemical element. We learned that when atoms of a chemical element are arranged in different ways, allotropic forms of elemental substances with different properties are formed. However, the variety of materials that surround us far exceeds the variety of elemental substances in all their allotropic forms. That is because the vast majority of materials are chemical compounds that consist of atoms of two or more chemical elements bound together in well-defined proportions. Note that what chemical compound we have is determined both by which elements form it and by the proportions of the numbers of atoms of different elements to each other. For example, carbon dioxide is a compound that consists of one carbon atom to every two oxygen atoms. In other words, has a 1:2 proportion of the number of carbon atoms to the number of oxygen atoms. It is a gas that forms in the process of respiration and is non-toxic to humans. On the other hand, carbon monoxide is a compound that consists of one carbon atom to one oxygen atom. In other words, has a 1:1 proportion of the number of carbon atoms to the number of oxygen atoms. It is a toxic gas, and inhaling any considerable amount of it can be deadly to humans and animals. Building and fire codes commonly require that carbon monoxide detectors be present in buildings to alert occupants of the presence of this gas. Despite being made up of the same elements, carbon and oxygen, carbon monoxide and carbon dioxide are very different substances with different properties because the proportions of the number of carbon atoms to the number of oxygen atoms in them are different. The observation that a given chemical compound always has the same proportion of the same elements was first stated as a general law in 1794 by the French chemist Joseph Proust. It is known as the law of constant composition. Let's take a closer look at this law to better understand what it means. First, consider two paintings. Girl with a Pearl Earring by the Dutch master Johannes Vermeer and a 1930 self-portrait of Mexican artist Frida Kahlo. Let's break down what each of these paintings shows. Vermeer painted a girl who is wearing one pearl earring. Thus, the ratio of the number of earrings to the number of girls in this painting is 1:1. Frida Kahlo painted another girl herself wearing two earrings. Thus, the ratio of the number of earrings to the number of Fridas in this painting is 2:1. Now, let's say we made several copies of each of these two paintings. The total number of earrings in all copies of the Vermeer painting is the same as the total number of girls, no matter how many copies we have. In other words, the proportion of the number of earrings to the number of girls is 1:1, regardless of how many copies we have. There is always one earring per girl. If another copy is made, it adds one girl and one earring. The total number of earrings in all copies of Frida Kahlo's self-portrait is always 2 times larger than the total number of Fridas. For example, if we have 3 copies of the painting, we can count 3 Fridas and 6 earrings. Therefore, the proportion of the number of earrings to the number of Fridas is 2:1, regardless of how many copies we have. There are always 2 earrings per Frida. If another copy is made, it adds 1 Frida and 2 earrings. In both cases, we have been replicating a basic unit, one painting, and this meant replicating all of its components, the girls and the corresponding earrings. When we did this, the ratio of the number of earrings to the number of girls did not change, although the total number of girls and the total number of earrings did change. The same observation holds true when instead of a basic unit that consists of a fixed number of girls and earrings, we take a basic unit that consists of a fixed number of atoms of different chemical elements. For example, zinc oxide is a compound in which the ratio of the number of oxygen atoms to the number of zinc atoms is 1 to 1. Therefore, its basic unit consists of 1 zinc atom and 1 oxygen atom. If we replicate this basic unit, we can get larger amounts of zinc oxide, but in any sample of zinc oxide that we take, regardless of its size, the number of zinc atoms will always be the same as the number of oxygen atoms. In another chemical compound, silicon dioxide, the ratio between the number of oxygen atoms and silicon atoms is 2 to 1. Therefore, its basic unit consists of 1 silicon atom and 2 oxygen atoms. If we replicate this basic unit, we can get larger amounts of silicon dioxide. But in any sample of silicon dioxide that we take, regardless of its size, the number of oxygen atoms will always be twice the number of silicon atoms. In yet another chemical compound, aluminum oxide, the ratio between the number of oxygen atoms and aluminum atoms is 3 to 2. In other words, there are 3 oxygen atoms per every 2 aluminum atoms. This is actually equivalent to saying that there are 1.5 times as many oxygen atoms as aluminum atoms, but in chemistry we always write whole number ratios. The basic unit of aluminum oxide consists of 2 aluminum atoms and 3 oxygen atoms. If we replicate this basic unit, we can get larger samples of aluminum oxide. But in any sample of it, regardless of its size, there will always be 3 oxygen atoms for every 2 aluminum atoms. Many chemical compounds consist of more than 2 elements. For instance, sucrose, table sugar, consists of carbon, hydrogen, and oxygen atoms. The law of constant composition also applies to such compounds. In sucrose, for every 12 carbon atoms, there are 22 hydrogen atoms and 11 oxygen atoms. So the ratios of the number of carbon atoms to the number of hydrogen atoms to the number of oxygen atoms are 12 to 22 to 11. A basic unit of sucrose consists of 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. The law of constant composition is one of the most important laws in chemistry. We must always remember that what chemical compound we have is determined not just by what elements it is made up from, but also by the ratios between the numbers of atoms of all these elements.